Hello guys, thank you for joining me today. It is another day where I am going to present a video teaching a little bit about nuclear. So in this module, let's go over the title. This is technical overview of recent development in small modular reactor, right? And specifically, this is the midterm presentation. So for this presentation, I am going to talk more about the 6 types of modular reactor, the small modular reactor that we have right now. And when I say small modular reactor, what is that? That is a nuclear reactor, right? There's a lot of talk about it, a lot of buzz about it, because the rise of AI, the rise of green energy, so we need more cleaner and green energy. We need more energy that's more sustainable and constant to deal with all the data centers and all the new technologies coming out. So one of the biggest solution right now is small modular reactor because it is very portable. It can be built at a factory and it can go anywhere. So a little bit of background of what this presentation is. This is an Oregon State, this presentation is for my class in Oregon State University, specifically NSC 505. And this is, although this is made for the professor, so that she would be able to watch my presentation and get me grade on it. I am posting it on YouTube so that anyone can watch it, even the YouTube audience. So I'm going to be more tailor this toward the YouTube audience as well. So someone who doesn't understand anything about nuclear or small modular reactor or nuclear power, this is kind of more for you, but I'm going to present it for a grade as well. This is a 2-credit class. So I'm not going to go into deep science into it, like, how does the nuclear fission or fusion work and what kind of elements, we're going to go gloss over, like the 6 basic types of modular reactor. For the final presentation, the topic is going to be the same, but it's going to go into a different kind of aspect of it. So for this one particularly, it's going into the six types of modular reactor. All right, so I do have a script on the other screen, so if you see me looking back and forth, that's why. Let's go into this. Oh, right, I'll talk more about this at the end as well, but I'm doing a master's degree in radiation health physics. If you don't know what a health physics is, that is a degree in nuclear physics or nuclear engineering with a more focus on like healthcare and how radiation affect a human body, and like more of a radiation protection type things than actually creating like thing. But there's a lot that overlap with nuclear engineering and nuclear physics for sure. So let's go into it. So let's go with the introduction. What are small modular reactor? I'm going to try to make this short. I don't want this to be a 30-minute long. So we're going to go through it. Right, small modular reactor are reactors that are small. They usually are built in like a factory, and you can ship it. It doesn't need to be built on site. Then you just go over there. You create the infrastructure a little bit on site, and then you kind of like Lego brick it together over there. That's usually kind of the main idea. There are 6 types, like I said. There ranges in size and whatnot, but it's different from like your regular traditional nuclear reactor with these huge cooling tower that you see. Those are extremely expensive to build. They require a lot of maintenance, and so this is kind of more of a solution for maybe a smaller setting, and you can even build multiple of them together in multiple locations and kind of feed, and eventually it build up to the same power level. But the main difference is definitely the size, right? Because SMR, which is the acronym for small modular reactor, the S is the small, is that the key word there. So there's a few different types. The purpose of this is they're clean, they're reliable, has low carbon energy footprint, right? They're very green, for sure. So the key benefit of SMR versus like your traditional nuclear reactor or power plant is they're scalable and they're very flexible in deployment, right? They're shorter construction time and lower upfront costs and enhanced passive safeties, right? So theoretically, they should be safer than your traditional plant, so that you won't see that much of a meltdown as much, theoretically speaking, right? Current trend is like there's right now there's around 70 SMR design under active deployment worldwide, right? And US has like around 18 active designs right now. So, yep. So the people that are very interested in it are who, like, of course, us, the United States. We have huge manufacturing AI tech industry. Of course, China, because they have huge manufacturing industry. They're like the second world power, right? And they also looking for application in not just manufacturing, but also in like military. Also, Russia also have a huge interest in that as well, among other countries as well. So let's start with the first type. So that's the land-based water-cooled SMRs. So like these are the PowerPoints. I'm gonna gloss through them. I'm not gonna go through every single point. So that's there for you guys to kind of reference. But I'm gonna talk about my knowledge in it, and maybe you guys can get a little bit more. And everything on the screen you can read yourself as well. So we're a land-based water-cooled reactor. So they're, like its name is, on land, and it's using water to cool it, right? So that's kind of more of a traditional type at most. Nuclear power plant, they're usually water cooled. So either there are PWR, pressure water reactors, or BWR, boiling water reactors, right? That's the main type, and pretty much what they use is just water to cool it, right? Those are kind of more of a legacy type design. So this is like I said, it's an older technology. But it's being used in newer ways. So the technology is improving, right? But you're improving on old technology, so it's easier to get licensing, and it has more of a data on what is safe and what is not safe. The data is there more, right? Versus all the other type of modular reactors that we're going to go over, where technically, theoretically, they're safer, but we don't have a lot of data to kind of, because theoretically and in practice are completely two different scenario, right? The power range for these type are around 50 to 300 MWE, right? And the advantage of these are they use established supply chains, right? So a lot of technologies are already there, so you don't need to create new technology for it. Higher capacity factors, right? And ideal for urban and industrial grids, because the technology is already in there. It's legacy type technology, so you don't need to adapt anything really for that. So there's a few like nearing construction. So like I said, this is our legacy type of technology. It's easier to be approved for sure. So I think there's going to be a bunch out in 2025 and 2027 at the latest. So this is a very traditional one. The cons of it is because it's using water. You have that risk of like hydrogen explosion, right? With Chernobyl and 3 Mile Island, Fukushima. Those all use water cooled, right? Technology, and with water, right? Because water is hydrogen and oxygen. Like when you put them in this type of high environment, they can energy environment, they can cause the hydrogen and oxygen to separate, and the hydrogen, of course, is very flammable, and that's what caused the explosion, is the hydrogen, right? Not the nuclear itself. Misconception, right? It's not a nuclear bomb. Usually it's a hydrogen bomb that spread everything to the atmosphere, right? The stratosphere, and that would really cause the damage and whatnot, right, to the environment. So water cooled, the cons of it is that, right? But with the technology today and the supervision and whatnot, it's not as dangerous as it used to be, right? The technology has improved so much, right? So marine-based water-cooled SMR. So it's pretty much what we use on aircraft carriers and submarines, nuclear power. But this is kind of more on civilian side. It's used to power floating vessels, so like cargo ships and whatever type of ships that you need. So anything that used for transport. So instead of using diesel engine that requires a lot of fossil fuel to operate and extremely environmentally destructive to operate, switching it with nuclear power plants on board can really help with clean energy, right? So like the water, this is going to be water cooled as well, but it's going to be on the marine type vessels, right? Same technology, right? And I think the biggest thing is getting it approved, right? A lot of people are afraid that, oh, well, a bunch of civilian vessels now has nuclear power, so what would happen if a pirate takes it? Usually not a lot can happen with it. Nuclear is really, really not, you're not magically going to have nuclear weapons just by stealing nuclear power plant, right? Because the refinement is completely different. Usually it's like 5% or under 5% refinement enriched uranium versus like when you need to make weapons grade, you're looking at 90%. So there's really not a lot there in regards to what people fear is. You know, the output, like I said, is 35 to 125. This is usually smaller than the land base. I think the pro, like I said, is saving the environment. You know, like it can allow the operation of these vessels without being refueled for a lot. So that could save a lot on the overall fueling cost, but the upfront cost is quite a bit to put these reactor in. That is a big hefty sum of change versus just putting in a diesel engine, right? But these the life cycle can last up to 10 years, right? A lot of them are built with containment in them, so they're not really built to be the fuel to be switch out at all. So when it's done, there's like a certain little component where you just take it out, you throw it out, and you put in a new reactor in, right? So that's kind of the design that I've been reading up on. Of course, there might be some other design that allow you to replace the fuel pellets. So there's a few example, right, that's been listed there. I'll let you guys read for sure, but the safety, like there's low power, self-contained like pressure water reactors with onboard cooling and refueling in port, right? And like from what I read, a lot of them has really good safety things there, where if you lose power to cooling pumps, they actually can dissipate heat by themselves with their different design, right? So it won't cause like the Chernobyl incident as well, right? So like the main question, like, oh, what happened if it hit the iceberg, right? And like, what if it sank to the bottom? And what do you have the nuclear meltdown? And I think from what I read, no, they have already thought about it, right? Of course, with all these pictures, I have the reference to it. So if you guys want to go and read some more on these type of things, they're very interesting. So go ahead. Last thing is, what are these marine type? What do they do? So instead of having like the traditional diesel engine type things where it goes to turn the propeller, this would generate electrical power, and it would generate a electrical turbine, which allows it to have more modular type turbine where you could add more but smaller, and it can be more like you can customize it a little bit better, right? But these modular reactor does take up pretty big amount of room on the ships as well. So there's a pro and con to be way in there. So yeah, but they're very interesting for sure. So now let's go to gas-cooled SMRs. So what are gas-cooled SMR, right? So they use usually helium, sometimes carbon dioxide, right? Like just air, but usually helium, right? And the reason that they use helium to cool these SMR type reactor is because helium are not reactive. They are noble gas. They tend to not, they're not explosive at all. They can't be. They're noble gas. They don't tend to want to mix with other elements, right? They're happy just being by themselves, right? So they're not very reactive. The con with it, and what they use these helium gas for is to like cool down the reactor. The problem with these like high temperature gas reactors, like HTGR, right, the gas cool reactor, is that helium is not very good heat conductor. So they don't cool the reactor as well as other type of reactor, even water, right? So these are a lot less efficient in cooling. And when you learn a little bit more about nuclear power, you're gonna realize that nuclear power, to be able to generate good energy and whatnot, you want to have it at a cooler temperature, right? The temperature, like I said, is like around like over 750 Celsius. That's really, really high. compared to like, let's say, other type of reactors that we'll get into, like molten salt, even like water cooled molten salt or liquid metal cooled reactor. So these tend to run a little hotter, but they have better safety because you don't get the hydrogen explosion like the water cool that you would have, right? And from what I have read on these type of reactors is that even though there's like a failure in, let's say, cooling pump, they tend to be able to dissipate heat by themselves. They'll dissipate heat into the environment by themselves. They don't really need the pump to be working. Let's say if these reactors are shut down, right? So they tend to be very, very safe, right? Yeah. So we are going to go into the next one, right? So liquid metal cooled fast neutron SMR, right? So the name for it is liquid metal cooled. And in the name, some people call it fast neutron SMR. They use fast neutrons, except there's different type of neutrons that are being shot out, right? So neutron is used to create chain reaction, right? So fast neutron can kind of do it a little bit better versus if you're like, let's say you have a water cool. And what I didn't say about water cool is water is a really good shielding type for neutrons, right? So when you generate a lot of neutrons and this type of water cooled tend to help with the shielding as well. It turned fast neutron into thermal neutron because of the hydrogen atom bouncing the energy around a little bit, slowing it down and making it into like slow neutron or thermal neutron. But these use fast neutron, right? And what's so good about fast neutron in a nuclear reaction, right? And in nuclear power plant, fast neutrons are more efficient, right? So that it creates a higher efficiency type reactor, so it doesn't have to burn as much. It doesn't have to burn as much fuel to get what you want to get out of it. So they're very efficient. From what I have read, they're extremely efficient. They create less waste, right? Because they're very efficient, right? You're not creating as much nuclear waste from it, right? Even though, like, I have my gripes about nuclear in the U.S., nuclear power in the U.S., where it's pretty much a bite of a Snicker bar and they're just throwing it out. You can refine it some more and you can reuse it, but that's just not what they do. They just want to throw it away. So this kind of addressed some of it so that you're taking a bigger bite of the Snicker bar, analogy-wise, right? So they have longer fuel cycle, right? It's 10 to 20 years versus just regular 10 years. And there's plenty of design. Challenges is handling radioactive coolant like sodium, right? So because sodium is one of the metal that they use, right? They use lead and a bunch of other type of metal, like lead bismuth as coolant as well. So that's what the liquid metal is. Yeah, let's move on. I don't want to make this too long. I can talk about nuclear all day long. I can make this a 24-hour lecture. To be honest, I love talking about nuclear, especially SMRs. This is kind of like something that I'm really interested in. This and space. So let's get back to the presentation. I don't want to make it too long. I'll lose people, especially on YouTube. My professor will watch it, but YouTube people, they have short attention span. No offense, but you know yourself, right? So molten salt SMR, right? Molten salt's very interesting. A lot of research going into it. When I was at Pacific Northwest National Laboratory, molten salt was a very, very big interest with a lot of people that I was with there. What the name of it is just you use salt to cool it. Now, is it table salt? Of course not. But salt get liquefied at a certain point of heat, right? So what is the benefit of molten salt? They transfer heat very, very well. They are a lot safer because they don't generate the hydrogen type thing combustion where the water cool would. So you theoretically it's a lot safer. It is very efficient because salt can keep the reaction cool even better than water can. And it operates at lower pressure. And that's the same thing for metal cooled as well. They operate at a lower pressure so that like you're not at as high of a risk as pressure explosion, right? So they're at lower pressure and higher efficiency, right? But let's go over the advantages. I didn't put the cons on here, but I'll tell you the cons, right? Excellent heat transfer and passive safety, right? We already talked about it. Ideal for processing heat and hydrogen generation, right? So you're not going to generate hydrogen, right? And create the hydrogen explosion where you would get from all these type of water-cooled reactor. Hence, what actually happened in Chernobyl was the water cooled, the hydrogen built up, and it caused a hydrogen explosion, right? So the cons of these are molten salts are extremely corrosive, right? If you live near the ocean, right, or the sea, you're gonna find that your truck or your car, they tend to rust a little bit faster because of the salt in the air, right? So the salt definitely corrode the metal a lot faster in these type of reactor, because these reactors are all made out of metal. So you need to put in what to resist it? Chromium, which is weaker and more. So that's the problem with molten salt right now, is just that they are corrosive to the metal that is being housed in, right? So that is the problem. Now let's go to the last one, microreactor. Right, so what are microreactors? They are ultra small. They're even smaller than most SMR that we talked about. They're very modular. They're portable. You just plug it in. So like, I think the main concept that I've been hearing about is for military bases, like overseas. So like, if let's say you're going to go over there and you're going to like build like a very short-term camp or base, you know, what can they use this instead of like, let's say a diesel or like generator, which would create a lot of noise, right? You can just plug one of these in, and yeah, they're extremely clean and efficient, and they are quiet, and that's the main thing, right? So it's factory built in a factory, transported by truck or aircraft, right? And it can be used in civilian as well if you have some project, something like that, or let's say there's a disaster area, right? So like, let's say there's a hurricane or tsunami or a freak earthquake that happened or tornado that happened, right? Like the disaster relief can just bring a few of these. Of course, because of the disaster, the power grid is all down. You can just plug this into the power grid and you can get some energy. Now you can plug them into series, right? Like into series or parallel, and then you can get multiple of them generate enough energy for the grid, right? They're good for remote-based disaster area, which is mining site, military outpost. We just talked about that, and can replace diesel generators, right? And that's kind of what it is kind of designed for. They have long life, 8 to 10 years. Of course, less than molten salt or definitely the metal cooled, liquid metal cooled, right? Passive cooling via heat pipe or gas, so you don't need. Like it could be air cooled, right, because of heat sinks or stuff like that. And there's a few that is being developed right now. When I was in PNNL, there was some chatter about Idaho National Lab or making something like this. But the cons of this, and we need to talk about the cons, right? I didn't put on the cons on the slide. But the con is they're extremely expensive to make. Like one of them is extremely expensive. They're very small. They don't generate a lot of power comparatively to the other SMR. The other SMR tend to be bigger. They can generate grid for like a pretty good like size city, right? But these are not there at all, and because of how small they are and how it is not as efficient at creating energy comparative per money wise, right? But a certain application it does work pretty well, right? So let's go on to our conclusion, right? So SMR represent a new generation of nuclear power. They're safer, smaller, and smarter. Smarter as in they can be more portable, and they're instead of having to build this huge gigantic power plant that requires a lot of people supervising it and maintaining it, these are a lot less to have to deal with, right? The benefit is they're very green, they're carbon free. They still need to take some carbon to produce these type of materials and whatnot, but they're a lot more green than your coal power plant or any type of power plant, really, even cleaner than solar and wind, right? Reliable energy for both developed and developing regions. So undeveloped regions, so let's say there's a disaster in Haiti, We could just bring one of these like modular reactor, or and we can just plug it into the grid. It's really easy to build. We can build it in the factory and just transport it on a boat, right? So like there's over 20 countries right now pledged to triple their nuclear capacity by 2050, which is going to be good because it's gonna create cleaner air for all of us that need to breathe. That should be all of us. And the focus is just licensing. When you go into like nuclear, if you ever look at the 10 USC for licensing, and of course when you have transport, that's another whole set of it. The licensings are so complex, and if you're going to other countries, different states, right? So maybe we should focus on just making the licensing and all these different things, the regulations, a little bit more streamlined, right? So not all as much conflict between different agency and whatnot. HALEM, helium, fuel supply. So those are high energy. I forgot something, enriched uranium. Those are the enriched uranium that we need to use for fuel. I forgot the acronym right now, but it's pretty much enriched uranium that you need to have it. The problem right now is there's just not enough supply of it, because not a lot of people are enriching uranium for it, because when you talk about enriching, people get very, very nervous. Now we're talking about for these up to at most 20%, at most, but we're looking at probably under 5%, right? That's in how enriched it has to be, right? When you look at weapon grade, you're looking at 90+% of enriched uranium. So there's a difference between power generation enrichment is just 5% versus like 90% for nuclear bomb, right? So there's a difference there, but the process is kind of similar in a higher scale. But that is a discussion for another time, because I don't want to talk about that type of because that's going to be a whole nother hour talking about it. So that proven economic competitiveness and scaling development. So nuclear is more expensive than like your traditional fossil fuel. Of course, this is just like upfront, right? But then long term, because they last so long and you don't need to keep generating, they actually pay off more. So I think whether you want to look at it long term or short term, like long term wise, they tend to be cheaper. But short term wise, if people are very short sighted, they tend to go for fossil fuel, because it's just lower upfront costs, right? SMR bridge, okay. So I just made a note down here just to say what I need to say, right? I put in the parentheses. So SMR bridge the gap between today's energy needs and tomorrow's clean future, right? So that's kind of summarized quite well, right? I think nuclear is the future, right? It's definitely not solar or wind. It just doesn't generate enough power, and its sun goes down at night, and the wind does not always blow, right? So nuclear power can always generate power, right? So I have a bunch of references. I have 3 pages of references. If you need to pause the video, okay, I'm gonna do 2 seconds. 1, 2. If you need to pause the video, reference 1, 2. If you need to pause the video, and third slide 1, 2. So there's all these references to. There's quite a bit. I had to do a lot of research into this slide particularly. There's a lot there, but let's go into conclusion. So that's the end of the presentation. Thank you guys. I'm just going to talk a little bit about what this college is. So I'm in the School of Nuclear Engineering, like the School of Nuclear Engineering and Sciences at Oregon State University. If you're interested in this program, I would look into it. They do have a bachelor all the way to a doctorate level at Oregon State. Oregon State worked for me because it's online, and I have a very big a really busy schedule. I'm a college professor teaching undergraduate math classes right now, so I cannot go to school full time and do that. But like they do have in-person classes as well. If you're interested, look at Oregon State. Of course, there are other states and other universities that offer this as well. I got accepted to many schools before I settled into Oregon State. Some even higher name, like let's say Oregon's, let's say Johns Hopkins and Rice University, but I just find that Oregon State just works better for me, and it fits my culture. I like the culture better. So that's what for me. For you guys, if you guys are interested in this type of program, if hopefully my lecture and my presentation for those who are watching on YouTube who are not my professor, it encourages you to pursue this career field, and that's why I'm putting it on YouTube and not just submitting it directly to the professor. It's just so that maybe I can inspire someone to go into nuclear power, because we definitely need more people in nuclear engineering as well, in the nuclear field as well, not just us, and range all the way from health physics, medical physics, you know, in the hospital, to nuclear engineers at the power plant or in the US Navy and whatnot. So definitely a huge demand for that. All right, guys, if you have any question in regards to SMR or nuclear or whatever I'm studying, put down a comment below. I will see you guys next time when I do another presentation, right? And I'll make videos other than a presentation in nuclear later as well. All right, guys, don't forget to comment if you have any question or if you just have any thoughts on it. And like and subscribe, right? So when you like it, it just makes it easier for other people to see this video. I don't get paid on YouTube at all. I just want to kind of give this information to other people. And when I was looking up this information on YouTube, there's nothing on these type of nuclear SMRs, right? There's just nothing there. Like I think this could help a lot of people if it can get some traction. All right, guys, peace out.